All right, so we'll pick up with 1.5 here. We're talking about transformations, and there's three kinds of transformations. There's shifting a graph, reflecting a graph, and then vertically stretching or smashing a graph. So we looked at shifting a graph in the last video. Let's take a look at reflecting a graph. Okay, suppose I have the square root function right there. That's that graph. I'll give you two functions to graph, which I'll call h and k, and then based on what we see going on there, we'll write up a general statement about this type of transformation, which is going to be reflecting a graph. Okay. So what if I want to graph h of x equals negative the square root of x? I'll use the table of numbers to do that. Like if I let x be 0, and by the way, I don't want x to be a negative, right? Because the square root of a negative, that's not a real number. 0 is fine, right? Because the square root of 0 is 0. So 0, 0 would be on the graph. If x is 1, the square root of 1 is 1. That'd be a negative 1, though, coming out of this. So the point 1, negative 1 would be on the graph. If x is 4, the square root of 4 is 2. That'd be a negative 2 coming out of this. So 4 and negative 2 would be on the graph. And yeah, if I don't have a calculator, I'd want to use nice numbers, ones that I know the square root of off the top of my head. It's like if x is 9, the square root of 9 is 3. That'd be a negative 3 coming out of this, though. So the point 9, negative 3 would be on the graph. And then when I draw this curve, it'd be flowing downward and towards the right into quadrant 4. Okay? So what happened to the original basic function y equals the square root of x to get the graph of h? Well, it looks like all I did was I reflected the graph about the x-axis. Why the reflection? Well, the negative in front of the function is causing that. Okay, so let's try another example. Like what if k of x is equal to the square root of negative x? Well, first of all, what's the domain of k? So I don't want the square root of a negative, right? Therefore, x has to be a negative because the opposite of a negative is a positive. Now, if x is 0, that's okay. The square root of 0 is 0, so 0, 0 would be on the graph. After we choose 0, we just want x to be a negative. So if x is negative 1, the opposite of negative 1 is 1, and the square root of 1 is 1. So the point negative 1, 1 would be on the graph. If x is negative 4, the opposite of negative 4 is 4, and the square root of 4 is 2. So negative 4, 2, that would be on the graph. If x is negative 9, the opposite of negative 9 is 9, and the square root of 9 is 3. So negative 9, 3, that point would be on the graph. Okay, and this curve is going to be starting at the origin and curling upward and outward towards the left into quadrant 2. So what happened to the original graph of y equals the square root of x to get the graph of k of x? Well, it looks like all we did there was we reflected all these points about the y-axis. Why the reflection about the y-axis? Well, it's the negative that's causing that to happen. Okay, so here's in general what's going on. Let's let f of x be a basic function. So here I'm using the square root function. Okay, what I'll say next is going to apply to any basic curve. If I throw a negative in front of the function, like I did here, so we saw on this graph that you're going to reflect all the points about the x-axis. Okay, in general, that is always going to happen. You're going to reflect all the points about the x-axis. Okay? If, in item 2, if I essentially replace x with a negative x, that's all I did there with k of x. Okay, I'm replacing x with a negative x. And we saw that you reflect the curve about the y-axis. Okay, in general, that's going to happen. Okay, so negatives mean reflections. Now, what if I had the function f of x equals the opposite of the square root of negative x? Okay, well, the negatives don't cancel, right? Because one's in front of the radical and one is underneath the radical. But in this problem, you're going to have two reflections, right? Like we're going to start with the graph of y equals the square root of x. We're going to rotate it all about the x-axis and then rotate it about the y-axis. So our answer is going to be a curve that's in quadrant 3, heading downward and outward towards the left. Okay, 0, 0 would stay at 0, 0. Here is 1, 1. So 1, 1, you go across the x-axis, that'll put you at 1, negative 1, and then go across the y-axis, that'll put you at negative 1, negative 1. And here's the point for 2. So when I go across the x-axis, that's going to put me at 4, negative 2. And when I go across the y-axis, that'll put me at negative 4, negative 2. Okay, so all these points are going to move. By the way, if I'm only reflecting a graph, it doesn't matter the order of the reflections. So here I'm going across x first and then y second. Like I go across y first and then x second. All the points would land in the same spot there. Okay. So that's the second type of transformation. We have shifting a graph, and then we got reflecting a graph. Okay. Now we're going to talk about vertical stretching and compressing of a graph, or compressing and shrinking of a graph is the same thing. And for this problem, suppose I have the absolute value function. That's a V-shaped graph centered at the origin. The V is facing upward. And now, unlike the last two transformations, let's go ahead and graph h of x and k of x, but I'm going to graph them on the same curve, right? Because if we look at all three of these curves on the same graph, we'll be able to identify what's going on with the transformation better. H of x is 2 times the absolute value of x, and k of x is 1/2 times the absolute value of x. So if I let x be 0, 0, 0 is on the graph. Okay, if x is 1, the absolute value of 1 is 1, so there's 1, 1 on the graph. If x is negative 1, the absolute value of negative 1 is 1, so there's negative 1, 1 on the graph. If x is 2, the absolute value of 2 is 2, so there's 2, 2 on the graph. And then if x is negative 2, the absolute value of negative 2 is 2, so there would be the point negative 2, 2 on the graph. Okay, and we have this V-shaped curve. Now, let's go ahead and draw the graph of h of x. So, I'll just use these same 5 numbers that I used to graph f of x, to graph h of x and k of x. Okay, so like if x is 0, 2 times 0 is 0, so there's 0 zeros on the graph. If x is 1, the absolute value of 1 is 1, 2 times 1 is 2. So 1, 2, that point is on the graph. If x is negative 1, the absolute value of negative 1 is 1, times 2 is 2. So the point negative 1, 2, that point is on the graph. If x is 2, 2 times 2 is 4. Okay, and so the point 2, 4 would be on the graph. And then if I let x be negative 2, the absolute value of negative 2 is 2. 2 times 2 is 4. So there's the point negative 2, 4 on the graph. Okay, what we're drawing is a V. You know, the absolute value bars give that away. And so I would draw this curve passing through these points. Okay, and that would be a sketch of h of x. Now, what happened to the original basic function, f of x equals the absolute value of x, to get the graph of h? Well, it looks like we took the graph of y equals the absolute value of x, and we stretched the graph out vertically. So if you imagine hands pulling on the vertical axis there, stretching this graph out, that's going to force the graph to get closer to the y-axis on both sides. Okay? So we call that transformation a vertical stretch. Now how about k of x? K of x is 1/2 times the absolute value of x. So if I let x be 0, 1/2 times 0 is 0, so there's 0 zeros on the graph. If x is 1, 1/2 times 1 is 1/2. Okay, so 1/1/2, that point is on the graph. If x is -1, the absolute value of -1 is 1, times 1/2 is 1/2. So there's the point -1/1/2. If x is 2, 1/2 times 2 is 1. So here's the point 2, 1 on the graph. And if I let x be -2, the absolute value of -2 is 2, times 1/2 is 1. Okay, so there's the point -2, 1 on the graph. And I'm drawing a V. Okay, so I draw the curve passing through those points there. Okay, and now we call this transformation a vertical compression, or a vertical shrink. That means the same thing. And what we mean by that is if you imagine hands, again, pulling on the y-axis, the vertical axis, smashing this graph of the absolute value of x, if it smashes the graph, then that's going to force the graph to split further from the y-axis on both sides. Okay? So here's in general what's going on with vertical stretching and compressing of a graph. Suppose that y equals f of x is one of the basic functions, one of those 8 functions that are on the sheet there. So like here I'm using the absolute value function. What it'll say next is going to apply to any one of those functions. And c is a real number. Okay? If we have y equals c times f of x, then that's going to be a vertical stretch or shrink of the graph. In general, you're going to be stretching the graph out if c is bigger than 1. So like here, c is 2. Okay? And we stretch the graph out by a factor of 2. You're going to have a vertical shrink or vertical compression if c is less than 1, but c is still positive. So like here, c is 1/2, and that we smash the graph there to get the graph of k of x. Okay? But if c is 1, then you've done nothing to change the graph. Right? If I'm just multiplying the function by 1, that's not going to change anything. If c is bigger than 1 means that you're going to have a vertical stretch of the graph. The bigger the c value, the more stretched out the graph will be. So like if I were to graph, y equals 4 times the absolute value of x, I would have a graph that's more stretched out than the graph of 2 times the absolute value of x. Okay? Now, vertical compression would happen if you're less than 1 but still positive. If c is 0, 0 times anything is 0, right? So y equals 0, that'd be a horizontal line on the y-axis. We're not doing anything with horizontal lines here. Okay? But if c is between 0 and 1, like if c is 1/2, then you've got a vertical compression. And so you're going to be smashing the graph. And the curve would split further from the y-axis on both sides. Okay? Now, I didn't mention, like, what if c is a negative? Where do you know what happens when c is a negative? we have reflections. So sometimes in this transformation, you might actually be talking about two transformations. If I were to graph y equals -2 times the absolute value of x, then I am stretching the graph out by a factor of 2, and also I'm going to be flipping the graph upside down. Okay, so the v would be in quadrants 3 and 4. Okay. Now, in general, like how do you get the new graph? Because just saying that you're stretching the graph out or you're smashing the graph, that's lovely, right? But like, how do I get the new graph? Well, all you're doing is you're going to multiply all the y values by c, which is sometimes called the stretch factor, to get the new graph. Okay, check it out. I have y equals the absolute value of x. That's this v. And in h, c is 2. Okay, so I need to multiply all the y values by 2 to get the new graph of h. 0 is 0. Well, when I multiply 0 by anything, I get 0, right? So that's me at 0, 0. Here's 1, 1. When I multiply the y value by 2, that'll put me at 1, 2. Here's -1, 1. When I multiply the y value by 2, that will put me at -1, 2. Okay, here's the point 2, 2. When I multiply the y value by 2, that puts me at 2, 4. And here's the point -2, 2. When I multiply the y value by 2, that puts me at -2, 4. So all I'm doing is I'm multiplying all the y values by 2 to get the new graph. Okay. Same thing with compression. So like c would be 1/2 in k. Okay, so what I'm saying is that if I multiply the graph of y equals the absolute value of x, all the y values, by 1/2, I'll be able to get the new graph of k. Okay, so 0 is 0. Well, 0 times anything is 0, right? So that's not going to go anywhere. But 1, 1, when I multiply the y value by 1/2, that brings me to 1, 1/2. Here's -1, 1. When I multiply the y value by 1/2, that brings me to -1, 1/2. Here's -2, 2. When I multiply the y value by 1/2, that brings me to -2, 1. And here's the point -2, 2. When I multiply the y value by 1/2, that brings me to the point -2, -1. Okay, so all I'm doing is, multiplying all the y values by 1/2 to get the graph of k. All right. All right, we'll go ahead and stop the video right there, and we're still in section 1.5. I'll get back to that section in the next one.